Sorry, view, present. Oh, my camera is, there we go. Hello, this is my Module 4 mastery assignment. Module 4 was on vectors and vector-valued functions, and also reviewed a bit of parametrics. So the first topic that we'll be talking about is differentiation of parametric equations. So some important terms are, what are parametric equations? They are a set of equations that describe the position of an object in terms of t, which usually represents time. And a parametric curve is the graph created by a set of parametric equations. And the parameter is the independent variable that is present in both parametric equations, which is, in almost all cases, so far at least, t. And parameterization is a set of parametric equations and the interval t values for which they apply. So it could say the position of a particle. The position of a particle is represented by the parametric equations x of and x of t and y of t, and for t is greater than or equal to 0 to less than or equal to 3. So it could just specify. So differentiation of parametric curves. So if x equals f of t and y equals g of t, then dy over dx is g derivative of t over f derivative of t. So since the derivative of g of t is dy over dt and the derivative of f of t is dx over dt, then dividing dy over dt by dx over dt will cancel the dt's in the numerator and denominator out, leaving dy over dx. Now, to find the second derivative, the formula is d over dt times dy over. So you take the derivative with respect to t of the first derivative, and what happens is that when you do that, since you're taking it with respect to t, but it's actually dy over dx, and that also creates a dx over dt. So to cancel it out, you have to divide it by dx over dt. So once you take the derivative of dy over dx with respect to t, you divide it by dx over dt to find the second derivative. So some examples are, if f of t equals 3t squared and g of t equals sine of t for all t on the interval of 0, 4. So the first problem is finding dy over dx. So what we'll do is we'll take the derivative of each function. So the first derivative of f is 6t, and the first derivative of g is cosine of t. Therefore, dy over dx is cosine of t over 6t. So that's how you would find that. So then for the second derivative of the parametric equations, you would have to find the derivative of dy over dx with respect to t, which would be t times negative sine of t, and negative t sine of t minus cosine of t all over 6t squared. And then, of course, to actually fix it, you have to divide it by dx over dt, which is 6t, because it's the first derivative of f. So when you divide negative t sine of t minus cosine of t all over 6t squared, you get the second derivative being negative sine of t, negative t sine of t minus cosine of t all over 36t cubed. And that is how you differentiate with parametric curves. So some important terms for our next topic, which is vector-valued functions. So vector-valued function is a function whose coordinates at a time t are described by the parametric equations as a vector, and position is an object's location at a given point in time. Velocity is the rate at which an object moves in relation to the time t, and acceleration is the rate at which the velocity is increasing. Speed is the absolute value of velocity, so you could have negative velocity as in you're going down, but you still have the absolute value of velocity. You're still speeding toward the ground, if that's a good way to think of it. So magnitude is the size of a vector, and displacement versus distance. Displacement is how far from the starting point you are. So let's just say you started right here, you went up like this, and then now let's just say you started right here, you went over, and now you're right here. Your displacement is only this far. Now, on the other hand, distance is how far you traveled. So distance is how far you traveled in that loop. So this is displacement, this is distance. So vector valued functions. Some parametric functions are written as a vector in the form of the positioner t equals the vector of x and y. That's the position vector. As with other functions, vector valued functions can also be differentiated. The velocity vector is simply velocity of t equals the vector of the first derivative of t, and the first derivative of f and the first derivative of g. And the acceleration vector, in the same manner, is, I should have put a of t equals, but it's the vector of the second derivative of f and the second derivative of g, and so forth. To find the derivative of a vector-valued function, you simply differentiate all equations in the vector. So some examples of vector-valued functions. The velocity of a particle is represented by the vector v of t equals the vector of 32t for the x value and cosine of t for the y value. Find the acceleration. So our first problem is to find the acceleration vector. So what we would do is we would differentiate the x value and the y value. So that would be, so the derivative of 32t is 32, and the derivative of cosine of t is negative sine of t, and that would be our acceleration vector. Now, one thing I probably should have said when doing the notes is that if you want to find something that's a higher order up, so let's just say that you have the velocity and you want to find the position, in the same way that we can differentiate them, we can also integrate them. So, and I should have mentioned that when I was in the notes. But the second problem is find the position vector if the position of the particle at t equals 0 is 0, 1. So we know that if we plug in t equals 0, let me see, my bad. So we'll take the integral of it, which would be 16t, which would be the integral of that is 16t squared plus c sine of t plus c. So now we have at t equals 0, I put the position, but it technically is the position, so that's correct, because it's not a velocity vector. The position is 0, 1, so if we plug in 0 into the x value, then we know that there's no y-intercept, because that would mean c equals 0. But if we plug in t equals 0 into sine of t, we get 1. Now, that means that it's actually sine of t plus 1. Now, that was a mistake on my part, because I was just thinking that, if you plug in 0 into sine of t, I was thinking cosine of t, so it would already be plus 1. So technically, the vector is 16t squared for the x value, and then sine of t plus 1 for the y value. I meant to do it the other way around, so that would be cosine of t in position, and so that would be cosine of t in the position, negative sine of t in the vector, and then negative cosine of t in the acceleration vector, but I messed that up. So yes, that would be sine of t plus 1. I apologize for that. Thank you. And that is the end of my presentation. Is it cutting off? Cutting off.